All right, everyone, we are back and we are going to do our Pset 5 solution. So, what material is the stiffest? So, basically the highest slope. I would say green. What about the toughest? Largest area under the curve? Probably red. Strongest in terms of UTS? That will also be, let's erase that here. I believe green just edges it out. So highest UTS, it also has the highest yield strength and the highest stress at failure. So good. Highest yield strength, green, just like you said. Most ductile, black. Most brittle, I think purple just edges it out there. Excellent. For the red curve, indicate what is the quantitative value of the strain at failure. So the strain at failure will be about 0.3, strain. The failure stress, which will be about, let's just say 1,000, let's say 1,100 MPa. So good. My yield strain, so the yield strain probably 0.01. Yield stress will be about probably 950 MPa. And ultimate tensile stress would be the same as this value here. Excellent. Now, I have the following mystery material under the stress rate below with an applied force of 10 kilonewtons. So 10 kilonewtons. Material is in a cube with rigid walls. And the shaded walls, so these walls here are physically attached to the red material. The top of the cube is open. The temperature and environment changes from room temperature to 100 degrees C. Thermal expansion coefficient is this. Thermal expansion coefficient does not indicate the material we're working with. And the final length in 2 direction is this. The final length in 3 direction is this. The cube has this length here. So we need to figure out what material we're working with, the stress and strain tensors, and all those values. So first step is our coordinate system. We're in the coordinate system here. Second step is material. We're not told what material, so Young's modulus and our Poisson ratio are unknowns. So we don't know what these values are. Now, let's write out the values for our stress and strain tensors. So I'm pushing my material here. So it's a cube with rigid walls, but the top is open. So when I push, I'm pushing in here. So there will be a stress in the 2,2, and it should be negative. As I push, I'm pushing in here. The temperature is also increasing. So the material wants to expand. So these walls are attached. So the strain in the 1,1 must be 0. There's a change in the dimensions in the 2 and the 3, so there will be a strain in the 2,2, there will be a strain in the 3,3, and we know each of those values. We also know the stress in the 2,2 because the stress in the 2,2 will simply be equal to my 10 times 10 to the 3 newtons over my initial length in the 1 times the initial length in the 3 direction in meters. So we know that as well. When I push in, the material wants to expand, and because temperature is increasing, there's also going to want to expand in the 1,1 direction, so there will be a stress in the 1,1, which we don't know what that is. Now, in the 3,3, is there stress? No, because the top is open, so there's no stress here. We can assume the rest of the walls are well lubricated, so we can now start to write out, let's log in again, Mathematica. Let's go ahead and start to solve these problems. I still have a little bit of a sniffle. If you're watching the dates here, in years past, you'll know Professor Steimel was not feeling well in October, mid to semi-late October. But anyways, enough of that. So let's go ahead. We know that our sig 2,2 is equal to, actually, let's go ahead and denote L naught 1 is equal to 10 times 10 to the minus 3. L naught 2 is equal to L naught 1. L naught 3 is equal to L naught 1. LF2 is equal to 9.99795 times 10 to the minus 3. I want everything in meters, SI. LF3 is equal to 1.12319 times 10 to the minus 2. And we know that my sig22 is equal to minus 10 times 10 to the 3 because we're in compression, divided by L naught 1 times L naught 3. And I know that my strain in the 22 is equal to LF2 minus L naught 2 divided by L naught 2. And then my strain in the 3 is equal to my LF3 minus L naught 3 divided by L naught 3. Excuse me. E1, I know this must be annoying. I apologize, but in fairness to me, I am actually not feeling well. Or not feeling well, but it's just what it is. All right, stop. Come on. E11 is equal to 0 here, and then my sig33 is also equal to 0. So we can write this out. 1 over y times sig11 minus nu times sig22 plus sig33. And then we can copy this. Just change this to 2, change this to 3, change this to 2, change this to 2, change that 2 to 1, and change this one to 1, actually 2, 1, change that to 3, change this to 3. So we've got our problem, but or our equations, excuse me, but we forgot one very important part, which is alpha times del t. Actually, we'll call it just ET, phone home, plus ET, plus ET, plus ET, because we need to account for the fact that there is this alpha, and we can go ahead and put this on here. Alpha is equal to 1 times 10 to the minus 6 to the minus 6. Our del T is equal to the final, so we rose from room temperature to 100, so 100 K minus 25. K or C, they're interchangeable because of that conversion, and then ET is equal to, and actually I'm going to clear, sorry. Excuse me, I'm just going to clear everything here. ET is equal to alpha times del T. And we can go ahead and just run this. And we have our expressions, we have our unknowns, so let's solve for everything. Make sure it all makes sense. E1, E2, E3. And 300 megapascals, about 0.2 for our Poisson's ratio, so we're dealing with a ceramic. Our sig11 is negative, as we'd expect. Fantastic. So we can answer the rest of these questions. What material? Ceramic. Full stress strain tensor? Got it. Principal stress values? So we can look at our sig11 is equal to this. Sig11. Sig22 is this. Sig33 is here. So this would be my sig1, the largest normal stress. Then my sig2 would be equal to sig11. And then finally my sig3, the most negative, is equal to sig33. Sig22, excuse me. Sig22. Fantastic. So those would be my principal stress values. Rotation to get to principal stress, 0. Maximum shear, 45 degrees. And then we ignore this problem. Excellent. Now, let's get to the next one. Working with mystery stent behaves like a polymer used to open passages and arteries. Thickness, thin-walled. So let's go ahead and I am going to behaves like a polymer. And I know we're skipping our coordinate system, but again, you will draw that for me. Polymer, so y equals 1 times 10 to the 9th. My nu is equal to 0.4. We are going to set that the radius is equal to 3 times 10 to the minus 3, because it's 3 times 10 to the minus 3, because its diameter is 6 millimeters. The thickness is equal to 10 micrometers, 10 times 10 to the minus 6. And r divided by t is such here. Let's make sure that is much greater than 10. So we are ready to go. It's thin wall pressure vessel. So sig H is equal to del P times R divided by T. Sig L is equal to sig H divided by 2. EH equals 1 divided by Y. Sig H minus nu times sig L. EL is equal to 1 divided by Y times sig L minus nu times sig H. We are told, all right, behaves like a polymer. Ooh, where is it? The stent is actually the orange curve seen here, but my undergraduates forgot to label the y-axis with values, but the x-axis is correct. Okay, that's good to know. Right at the full stress strain tensors at the point of failure. What is the pressure at the point of failure? What's the value of maximum shear, 3 principal stress values? So, at failure, we reached a strain of about 2, 4, 6, 8, 10. So, about 0.46, because it's 46%. So, that's basically telling us at the strain at failure, which is our hoop strain, we reached a value of 0.46. So that will give us our pressure. And with that, sig H, sig L, EH, EL. So those are my values. Excellent. So this one's done. What's the pressure point of failure? We solve for that as well. What's the value of maximum shear stress? It will be sigma H minus sigma L over 2. List the 3 principal stress values. Sigma 1 is equal to sigma H. Sigma L is equal, or sigma 2 is equal to sigma L. Sigma 3 is equal to 0, and that's always true for all values of basically. Actually, that's true for all thin wall pressure vessels. Excellent. 4 and 5 and then 6. Ooh, this is a nice problem set. I like it. Let's go ahead and let's look at number 4. So, Sylvester Stallone is hanging and he needs your help. He's basically, we have one Sylvester Stallone hanging on one side and one is on the other side. You can approximate the yellow material as on the cliff as a basically ceramic. So, let's go ahead. We're going to quit the kernel. Let's quit the kernel here. So our material is a ceramic. So y equals 300 times 10 to the 9th. Our nu is equal to 0.2. Excellent. Attach the wall. Started hanging. The temperature is increased. So our del T is equal to 43. Increase positive, so that's good. The force in the one direction is equal to minus 50 times 10 to the 3. Our force, it's that, basically, the final dimension, so LF3 is equal to 6.5 times 10 to the minus 3. Our L01 below you can see is 0.01. Our L02 is equal to 0.35. Our L03 is equal to 5 times 10 to the minus 3. Good. The force in the 3 is positive, and it's 85 times 10 to the 3. Excellent. So, right at the full stress and strain tensors. Also, Stallone is 100 kilograms. So, when we look at this problem, he is hanging here. So we have basically a mass, and basically you can kind of treat this as a shear stress on the edge here. So our force is equal to mass, which is 100 times gravity, which is 9.8. And that's, again, the normal would be in the one direction on the pot, and then we're pointing down here in the 3, the negative 3 direction. So it's going to be minus this, and this is our F in the 1, 3. So we can start to calculate some of these values. So sig 3.3 is equal to F3 divided by L01 times L02. Our sig 1.1 is equal to F1 divided by L02 times L03. And our sig 1.3 is equal to F13 divided by Let's see. It's acting on L naught 2 times L naught 3. If we look at that here, that's the area that it's acting on. Perfect. Fantastic. So let's start to draw out our stress and strain tensors. So we know, and we're going to have to keep into account our thermal strain too. So looking at the system, there is going to be a strain in the 3-3 because we're pulling it, it's going to extend there. There will be no strain in the 2-2 because we're constrained there. There will be strain in the 1-1 for sure. There's also going to be stress in the 1-1, stress in the 3-3. There's also going to be stress in the 2-2 because we have that constraint. The material, again, we're pushing in here, it's pulling here, but we're also wanting to expand out due to thermal expansion. So we know this, we know this, we don't know this, we don't know, actually we do know, and actually we also know sigma, excuse me, there's also going to be a sigma 1-3, a sigma 1-3, and there'll be a strain 1-3, a strain, 1-3. So let's see, we know sigma 1-1, we know sigma 3-3. We're also told we know that. We also know this, but we don't know our alpha. So 1, 2, 3 unknowns. And then these are all separate equations here. Fantastic. So I could also do E13 is equal to 1 divided by y times sig 1-3, actually, times 1 plus nu times sig 1-3. That's an independent expression. E1 is equal to, and I'm going to copy and paste these right up here. And then we'll define ET as well. Oh, no. Oops. That could have been a disaster. Save often. Del ET is equal to alpha times del T. So let's shift enter all of those. So, we need some E11 values. So let's say, for example, we know that E22 equals 0, E33 equals LF3 minus L03 divided by L03. Good, good, good. And now I can solve. So we have 1, let's define, why is L02? L02 equals this. Let's make sure that that's the case. Yeah, equals 3.5. So we have 1, 2, 3 unknowns. Excellent. So solve. Oh no, it's going to take me away from you all into Mathematica land. E1, E2, E3. So let's see if this makes sense. So the strain in the 1-1, in this one will actually in the stress in the 2-2, that makes sense, will actually be positive here. So we could actually see strain in the 2-2, strain in the 3-3. Good, 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 good. Excellent. So in this case, we are pulling in this direction. We're compressing here, but the expansion due to that constraint will actually push the material out and be positive here. So we have our alpha, and we see that our stress in the 2-2 is negative, which is what we may expect. So you can kind of see that cool part from those constraints. Excellent. So full stress and strain tensors, what's the rotation principle? 0. What's the value of maximum? What about maximum shear? Well, by maximum shear, if I look at the whole system, so if I look at sig 1-1, sig 2-2, which we know, and sig 3-3, we can kind of see that value here. F1, F3. We also should show right now what is our sig 1-3, our E13, just so that we have those values at hand and available to us. So we can see, actually we can calculate that, and our sig 2-2 is this. So sig 2-2 is equal to here. Fantastic. So our maximum shear stress for the whole system would be sig 1 minus sig 3. So let's look at those values. They're all, so it's going to be sig33, that's the positive, minus, what's the most negative? For sure, this guy, minus sig22, divided by 2. So sig1 minus sig3, and there you go. We got it. Rotation to principal stress, 0, and we have those, actually, ooh, is it 0? We've made a big problem, a big mistake. We've neglected something very important. We are in plane, we actually have a plane stress state. Actually, do we have a plane stress state? We actually cannot solve this problem. And why is that? Because we don't exist in plane stress. We have stress values everywhere here in strain, so we don't have the tools effectively to answer that question. So, yeah, we cannot solve that one. So, kind of a trick problem effectively in there. All right, let's continue working on here. All right, so now to one of my favorite questions that I really like. I love this problem. So first I'm going to go ahead and I'm going to quit the kernel, clear everything, make sure that we're all good to go. That last problem was very fun. I liked it. Little trick question hopefully makes things a little bit easier for you. So I weigh approximately 100 kilograms, and I'm standing on a polymer that's confined to, basically it's in a cube. We have those dimensions, and I need to figure out what temperature do I have to reach to ensure that when I step on the cube, that my position on the top of the box does not change. So if I'm standing on this box, there's going to be some deformation here. So I want to raise the temperature enough so that effectively my strain, 1, 2, 3, my strain of the 3,3 will be equal to 0. So I need to figure out what's my delta T, or the T final. Let's just say T final minus 25, like I'm at room temperature starting. So let's go ahead and let's solve that value. So we're going to have to do, let's see. I'm going to have to do one thing that I usually don't like you to do, which is, if it's a polymer, we're going to have to here actually assume a value because we're not given it, but we can use our notes. We could assume a value of our thermal expansion coefficient, and we actually need it to solve. Oh no, please come back. No, no, no. Oh, it's too bad. So let's go ahead. I'm very familiar with these notes. I should be, I wrote them. All right, so let's say polymers are, so my alpha is equal to 50 times 10 to the minus 6. Let's say that my Young's modulus is equal to 1 times 10 to the 9th. My nu is equal to 0.4. My ET, actually my del T equals TF minus 25. Let's say my ET is equal to alpha times del T. Excellent. So let's start to define. We also know that my E33 has to be equal to 0. If we are in a box, a rigid box, we also know that even if I stand on it, the strain in the 1,1 is also going to be equal to 0. The strain in the 2,2 must also be equal to 0 because we're constrained. I know that the sig33 is going to be equal to, actually let's do ahead. Our L naught, our side length, is going to be 15 times 10 to the minus 3. So my sig33 is equal to minus 100, which is my mass, times 9.8, divided by, I'm going to do L naught squared. So I'm going to copy these same expressions. We know that there will be stress in, once I step on this, stress of the 1,1, stress in the 2,2, stress in the 3,3. So let's shift enter. Let's see what we got in terms of our unknowns. So we don't know what the stress in the 1,1 or stress in the 2,2 or my temperature final is. So let's solve E1, E2, E3. And we can see that for our value, it takes about 42 degrees. Actually, basically, a TF of this 42 minus this, 42 minus 42.2 minus 25. So about 17 degrees if we take that value to basically prevent me from basically any strain essentially occurring in that system. So to keep me right on top. Awesome. It's amazing to me that it doesn't take much temperature once you have those values. All right, so we've got our final answer here. So let's go ahead, or final question, excuse me, not final answer. I'm working with the following material, chromium, which is seen here in red inside the cube. It should be noted that the top of the cube here and here is open, and at basically here and here, at those planes, they're attached. So during this applied stress state, the temperature increases from 500 K to 180 degrees C. And actually, that's not going to be. So let's go from 180. Actually, let's go ahead and calculate. Please ignore the increases there because that's a typo. 180 plus 273. And again, if you solve it a different way, it's no problem. So we're going from 500. So this is our del T is equal to 500 minus that. But if you minus 180 plus 23. So we're actually, our final temperature is actually flipped. So 500. So you can kind of solve the problem here. The thermal expansion coefficient is this value. So let's set this up. So that's our del T. Let's see, temperature increases from... just because it's increases, let's keep that positive. Again, you can solve it either way, but I'm just going to keep it as positive. Temperature is increasing. We're going to say ET, so alpha is equal to 57 times 10 to the minus 6. Our ET is equal to alpha times del T. Our, okay, let's see what else we're given here. Lubricated, we're also told that our L naught is equal to 20 times 10 to the minus 2. The LF3 is equal to 207 times 10 to the minus 3. So our E33 is equal to LF minus LF3 minus L naught divided by L naught. So what is happening here? So we're looking at, what is it? We're also chromium. So we also know that our Young's modulus equals 100 times 10 to the 9th. Our nu is equal to 0.3. Fantastic. So let's bring in our expressions here. Excuse me, but I know I'm trying to keep doing that, but all right, so we're good. All right, so if I look at this material, our stress and our strain tensors, so if we're attached here, the strain in the 2,2 must be 0. There is a strain in the 3,3, and we've already calculated it because luckily we're given that direction. When I pull here, and when the temperature, again, the top of the cube is open. Let's see here. So when we pull here, and when we basically allow that system to, and we're attached here, so we should expect that there's definitely going to be a stress in the 2,2, and we should probably expect it to be negative. There also will be, we pull up here, there also can be, as the temperature increases, there could be a stress in the 1,1 as well. There definitely is a stress in the 3,3. Here we go. And we see that as we pull up here, the strain in the 1,1. So if we're assuming that, and this is where this is actually a somewhat open-ended problem, because we can state, or we can think that if our temperature decreased, we'd actually be in a simpler state. But we're assuming that temperature increased, but we can't be sure since it's going to touch that wall. So because we're going from 500 to, I'm going to actually, let's solve it. The problem would just flip in the following ways if we keep it as, actually if we solve it as such. So if temperature is decreasing, that means when we pull here or pull here, there's going to be some strain in the 1-1, but there's going to be no stress in the 1-1. If you're assuming that there's a significant temperature increase where it's going to push up against the walls, then there'd be no strain in the 1-1 and there'd be stress in the 1-1. But we're going to solve it as such. So we're going to say that sig 1-1 is 0. We're going to say there is an E11. We're also going to say that E22 is 0. And we have our alpha. We have all those other good things. So let's go ahead. Actually, excuse me, an alpha of 57. Our del T is going to be the negative here. So not absolute. So when we solve this, actually, let's make sure. So we have 1-1, 2-2, 3-3. Makes sense because we already said we had this. So strain the 1-1, 2-2, 3-3 for stress. Good. So let's solve. And we're going to do solve E1, E2, E3. And we get a strain in the 1-1 that is indeed negative. Makes sense. A stress in the 2-2, which should be positive because it wants to resist that, and a stress in the 3-3 that's there. And we need to solve for the force. So it's going to be this equals force in the 3-3 divided by L0 squared, and that would be my force. So we can go ahead and look here. Applied force, we got it. Stress and strain tensors, we got it. Principal stress values, so again, rotation and principal stress, 0. Rotation maximum shear, 45 degrees. Maximum stress, let's do sig 1-1, sig 2-2, sig 3-3. Actually, sig 3-3 is here. Sig 3-3 is this. Our sig 2-2 is this. So our maximum shear would just be sig 3-3 divided by 2, because again, sig 1 minus sig 3, so the lowest values. And excellent, excellent, we got that. Write out the expression for calculating the strain in the 1-1 and the 2-3 directions. So we already wrote out the 1-1. 2-3 is equal to 1 over E times 1 plus nu times sigma 2-3. Calculate the stress in the 2-3 if the strain is 0.001%. So we could go ahead and solve that. So let's go ahead. So the stress, if we have this, so for example, I'm going to solve my 0.001 times 10 to the minus 2, because again, I got to get rid of that percent, is equal to 1 over y times 1 plus nu times sig 2-3. Solve it, and there we go. That is it. A very, very comprehensive problem set. I hope you've all done your best, but if you could do this, you're going to ace that exam. So we'll see you all next time in the next solution video. Thanks.